everyone. Welcome back to class. Great. Thanks, everyone, for being on time here. I was a little worried about you all getting here. I know last week you were getting used to the location, and they were running security up there. So I was starting a little late today to see what was happening, but it looks like everything's running much better. So going forward, we'll always start at 2:10 here and in the other room as well. So one announcement I already announced on Quarkus, Practical's moving to RS 303, the other MIE computer lab. It's not as good of a setup, I don't think, but I've been told that the ventilation is really excellent in that room. So we're going to move you all in there so you can have a little bit safer experience there. Are there any questions about practicals? I know a quarter of you did them yesterday. I didn't hear any issues arise. Any questions about anything else in the course? Yeah? How do you get to that room? Rosebrew building, I'm sure some people around you can direct you. Yeah. The next session is right after this. You'll have 200 of your peers headed that way after. Yeah. It's not far. Good. So today we're going to be covering the topic which I mentioned last time, which is called mobility. And today we're going to work just on the chalkboard. And last time we set up really fundamental that concept of kinematic pairs. And that was how links are connected together within a mechanism. And we saw there were 3.5 types of kinematic pairs. Can I hear any of our kinematic pairs? Call them out.
Sliding pair.
Okay, I hear some here. We had a sliding. I called that number 2.
Rolling pair.
Rolling. Yeah. I hear turning. And I heard 4-bar. Not right. And 3B we called as like a combo, slide plus roll. Okay, and those are pretty basic. No one, I think, here was surprised by seeing any of those. Sliding plus rolling is a weird one, and there were a lot of questions last time about that, which is natural. And I spent a whole lecture laying those out really carefully because those tend to be a source of confusion going through the whole semester. It's this really fundamental idea of how two links are connected together. Okay, they're not crazy things, but they're really fundamental for the course. And the first time that we're going to really start using them is today with mobility. So I'm going to define this concept of mobility, and we're going to think about it as how many different inputs would you need to a mechanism to drive it in a controlled way? Okay, that's our sort of a general definition, but I'm going to give you the more accurate definition here. We're going to use lowercase m. It's an integer number for mobility. Okay, and this is, I'm going to write it out here. It's the number of mechanism parameters. Okay, parameters, which I've used this before. Parameters are things like position or an angle. Position or an angle, so we could have like x or theta, other parameters. So those are numbers that describe something moving in our mechanism. So mobility is the number of mechanism parameters which must be independently set or fixed or specified. We're going to say theta equals 45 degrees, something like that. So it's the number of mechanism parameters which must be independently fixed to determine the state of the mechanism. Or we'll say to set the mechanism state. Okay, so if we have a car going down the road, it has 4 wheels, how many thousands of components in it, right? All I'm talking about right now is the motion forward and turning, right? So how many mechanism parameters do you need to know? If you're just looking at a car, let's say we set it on the ground, how many parameters would we need to be able to specify? That one's a little bit tricky, actually, because it can move in x and y, right, on the plane of the ground. So that's like 2. And it can move, another way of thinking about it is it can move forward and it can turn, right? So that's like another 2, another way of describing mobility. So that's a complicated one, but for mechanisms that move maybe rigidly connected to the ground somehow, we're going to be able to define this. The mechanisms I've shown you before, those 3 basics, 4-bar mechanism, slider crank, and cam, those all have a mobility of 1, which is going to be really common. We have one input, like a crank that was turning, and it set the whole mechanism into motion. Other more complex mechanisms, like a car moving on the plane, maybe you need multiple inputs. Gas pedal and steering wheel, 2 inputs to that mechanism. Okay, so this is mobility. I'm going to teach you how we can systematically look at a mechanism, calculate that mobility, and we're going to see what we're able to tell with this. It's going to be a powerful, quick look at a mechanism, which is going to be an important way to sort of sum up the character of a mechanism, and you'll be able to do it really quick with many mechanisms after a week or so. Okay, so we're going to start by looking at the basics. Let's look at a free link. So we're going to have a free link, which is just moving through space. Okay, and I'm going to draw a coordinate axis here. So we have x and y coordinates here. And I'm just going to call these 2 ends of my link A and B. So just these 2 points at the end of this link so we can describe where it's going. And we're just looking at planar motion here. Okay, planar motion just in the plane of this page. This whole concept you can extend to 3D, which we're not going to study a lot in this course, but it's pretty straightforward to extend things to 3D. Okay, this link, how would we describe its position on the page? That's what we mean by state. State is like the location of a link, or for a mechanism, the location of all the links. Okay, so there's lots of different ways you could choose, or parameter sets you could choose. Just like the car, you can describe by x, y position, but you could describe its velocity by the forward speed and turning rate, something like that. There's different choices, which some will maybe be better than others for various reasons. But let's just come up with some choices here. Okay, so one would be, let's track the x and y position of point A. I think that's a pretty nice one. So that's 2 parameters. So we're going to actually keep track of these parameters here. So parameters of this link, xa, ya. Another one we could track is the angle of this link. So I'll add theta on there. And if I tell you those 3 numbers and give you this coordinate system, and I tell you, I give you this link as a piece of metal, you could place it on the board, right? You would know its state, its kinematic state. Okay, and in fact, all links, okay, are going to have 3 parameters to start. So we're going to say all planar links have 3 parameters. Okay, and it doesn't have to be this choice of 3. You could choose an alternate set. Anyone want to tell me an alternate set? Not these 3 that would also specify. You can use point A or point B or angles. Yeah.
Like polar points or something?
Sorry?
Polar points? Like instead of Cartesian coordinates, polar coordinates?
Oh, polar coordinates. So that would be a choice. I'd have to redraw my graph though. So I'll get another one. That is a good alternate choice. Yeah.
Could you do either the x or y of b and that would imply the other?
Okay, using point B. So we could use, you said x or y. I'll just choose x. And what else would we need? We need 3, right? So which other, what?
And then y and x of a.
Yeah. xa and ya. Right, that would also, if you fixed those in place, that would also tell you where that would also constrain the location of that link. Now some of you may look at this and say, but let's say we set this one, the x locations first and the y location second. This one actually, there could be two solutions for this one, right? Let's figure it out for this one. So here's xb. Okay, and we set xa and ya. But we didn't set the angle and we didn't set the height of b. So there's actually another solution, right? The link could have been down here. That's like the alternate, we'll call this parameter choice 1 and parameter choice 2. So this is like an alternate solution for parameter set 2. So some coordinate choices, they would fix the link. Like let's say it was here, and I told you these values, and you held those parameters stationary. It would hold the link there. But you could take the link out and move it to this alternate choice, which would also satisfy those three, right? This first choice was better because it doesn't have two solutions. If I give you this choice here of 3 parameters, it sets the link. Okay, and this distinction or this little confusion is why my definition of mobility doesn't have to do with how many solutions there are. It has to do with how many parameters must be fixed, okay, to set the state of the mechanism, I'll be really clear here, also fixed. Okay, so think about it like how many inputs do you need to hold stationary to keep the whole mechanism stationary? Okay, we'll talk about multiple solutions, and this kind of thing will come up with mechanisms later on. Other questions about this?
Are we assuming that we know the length of the link? Or like
Yeah, you know the length of the link. Like I give you a piece of aluminum that is the link and it has A and B written on it. Yeah. Other questions about this? Yeah.
Another set of parameters you could use is x of one point and y of the other, and the angle the link makes.
Okay, this is the third set you're telling me here. Let me write it down while you're saying it. X of 1 point.
Not as good as the first set, because the first set you can just change any of those,
Uh-huh.
and they're not dependent on each other. But
So let's hear your points. XA.
xa, yb, and the theta.
XA, YB, and theta. YB and theta. Yeah. Yeah, that one would work as well, I think. So there's lots of choices. And for an individual link, you can come up with, there's not an infinite number of choices for an individual link, but there's multiple choices. And they could all fix the link in place. And for a mechanism that's made up of lots of links, you can make a list of 3 times the number of links of parameters. Okay? And our goal is now, we're going to investigate which of those parameters are fixed and which ones are free when the mechanism is moving through space. So this is what we're going to do now, is we're going to start adding kinematic pairs. So we're going to take our link, and let's just add our most basic turning pair. I think that's the easiest to look at. Okay, and I'm going to attach our turning pair at point A. So I'm going to call that turning pair A. Okay, so we have the same link. We'll call it link number 2. The ground we number 1 as always. Okay, so in this case, what happens? How many parameters would we need to describe the state of this link now? Anyone? Yeah, 1. Yeah, 1. And what would you choose?
Angle?
Angle's a really good one, right? That's an unambiguous one. Theta would be a good one. Yeah, you could use a different one, like the height of B, or the x-coordinate of B. That runs into the same multi-solution problem like this we had over here. But those would also fix the link. They may have a little multi-solution issue. At any rate, we only have 1 free parameter. So we only have 1 free parameter. So that means our turning pair restricted 2 of those parameters. Or the term that we're going to use, which I introduced last time, is constrains two parameters. So let's assume we were using my first definition, xa, ya, theta. Of course, the turning pair constrained xa and ya. Okay, but it leaves theta free. And so we're going to go through and classify all of our types of turning kinematic pairs. We have 4 types of kinematic pairs. We're going to classify all of these, and we're going to see how many parameters each of them restrict. And we're going to use this so that we can calculate the freedom or mobility of an entire mechanism all in one go. So I'm going to use this as my little chart here. Turning pair, one parameter is free. We'll make a little chart at the end if you don't have room in your notes to add another column there. So this is what happened with our turning pair. And so we're going to actually end up calling, I call it one parameter free. The term that we're going to use and the term that the textbook uses is a turning pair is called a 1 degree of freedom kinematic pair. One degree of freedom kinematic pair. And degree of freedom is a common word used in mechanism and especially in robotics. You'll see this word used a lot. It's how many different kinds of motion are allowed. Or what I've been calling it is free parameters. We'll call this a 1 degree of freedom kinematic pair. Yeah, question in the back.
Does that mean xb, yb, and theta are the same thing?
Does that mean xb, yb, and theta are the same?
Because you said one parameter is free. So are we only considering theta and not xb and yb since they can change?
Ah, yeah. So when you choose, that's a good question. You're asking, okay, I was talking about this parameter choice. Once you choose your parameters to describe a link, that's kind of set. That's how we would call it parameterized the problem. You've chosen those 3. So we don't need to worry about xb. We don't need to worry about xb, for example, if we've chosen that. Those are our 3 scalar values that we use to describe the state of this mechanism. I mean, you could also calculate what xb is separately, but that's not part of our parameter description that we've chosen. So that's something you choose up front, and then you can calculate which one is fixed and which one's free. Okay, any other questions about this one? So this is our turning pair. We're going to go through our other 3 types of kinematic pairs next. I don't want to hide everything here. So our next type of kinematic pair is a sliding pair. Okay, in the simplest way we think about a sliding pair, let's just put our link on the ground and have it sliding along the ground. So forget about the turning pair. We're going to do a new mechanism now where we put our link 2 on the ground. To make it really clear that it's a sliding, I'm just going to draw like a block here. Okay, and of course, the motion's pretty simple. It can slide back and forth. So if I wanted to choose one parameter to describe the motion of this, I'd say, let's put a reference point over here and say, okay, this dimension x is free. So the sliding pair has constrained our other parameters, right? So what has been constrained? The other 2. Y, we're going to keep using our same ones here, ya and theta. Right? The link can't rotate, and ya, the height can't go up and down. It's just sliding horizontally. Okay, so just like our turning pair, the sliding pair also constrained 2 parameters and leaves x free. So one parameter is free. two parameters fixed, it's the same story as the turning pair. So our conclusion here is that a sliding pair is also an example of a 1 degree of freedom kinematic pair. In degree of freedom, we're also often going to write DOF. That'll come up a lot in the course. DOF for degree of freedom. So sliding pair is another example of a 1 degree of freedom kinematic pair. See, I'm too used to SF1105. I can write on the top board. This one's a little taller, though. I can't reach it. So that one's also a 1 degree of freedom sliding pair. Any questions about that one? That one's more straightforward, I think. Yeah.
So when we were talking about the turning pair, you first started off with a free link and then you added the turning pair. So in this case, the free link was just the box, just two, and then you added sliding pair.
Yeah. So we started over. If we're talking about the sliding pair, we just take our link and say, let's put a sliding pair, make it slide on the ground. And I drew it like a box to make it really clear that it's just a sliding pair. Yeah. Okay, so let's keep going with our other pairs types. I'm going to keep going on this board so we can keep our chart over there. Next up is rolling. While I'm erasing here, I'd like you to think, how many free parameters are there for a rolling pair? I'll give you a hint. This one's harder to think about. Okay, so here's our link. I'm going to shape it like a circle now, just to make it really clear what's happening. I keep breaking the chalk here. Okay, so this is our rolling pair. You may say there's some issue. Anyone see an issue with my drawing? Thinking of last time how we drew them, yeah. You mentioned about matching the curvature. So last time I was drawing different examples of rolling pairs and roll plus slip with both curved surfaces. We could do that, but this one is fine as a straight. We need to draw on our drawing if there's slip or not here. If I don't draw anything, it kind of implies that it could be slipping. So we better write on there no slip to be nice and clear that it's pure rolling, just rolling along the surface like a nice rubber edge on there that doesn't slip. That's a rolling pair. Or it could be geared, like a rack and pinion connection with gears. Okay, rolling pair. Can anyone give me a thought? What is this rolling pair constrained or what is free? Let's start with constrained. What is fixed here? Yeah. The height is clearly fixed, right? That one's good. So why the height of this link is fixed? It can only go back and forth. But now we get into horizontal motion and rolling. And both of those can change, right? They're not fixed. But are they related? Is there a relationship? Let me draw this clearly. Let's put an actual dimension on there. We'll call that the x position of the wheel. I'm going to draw it to the center. You could draw it to the bottom connection point. It would be the same x. And theta is here. Are these related to each other? Yeah, they're related. What can we give an equation? Can someone? Angular velocity would relate, yeah. Can anyone give me an equation that relates x and theta? Let's assume that when x is 0, theta is 0. Yeah?
So x is equal to the arc length, so theta r?
Yeah, we need to know the radius. We'll call that big R. So x and r, x and theta are related by the equation you just told me, which is good. X equals r theta, right? Assuming x equals 0 when theta equals 0. Okay, so they have a relationship. So if we think about our definition of mobility, which is hidden right now, are both of these parameters free? Or if I tell you one of them, would that be enough to fix the whole location of the link? One is enough, right? If I tell you x equals 1 meter, you can calculate theta. Right? So because these two are related to each other by this equation, that means that there's only one free value between the two of them. So our conclusion here is going to be between the two, x and theta, you can choose one of them to fix. Once you choose one, it'll fix the other one as well. So between x and theta, there is one free value. Okay, so we don't have a special name necessarily for these variables which are related to each other. It comes up in many different ways and mechanisms. But anytime two of your variables are related like this, you can say they basically count like one now, right? If I tell you theta, you can calculate x and vice versa. So that means for this mechanism, you only need to specify one number to fix the wheel. So a rolling pair is another example, just like turning and sliding. Our final conclusion here, rolling pair is another 1 degree of freedom kinematic pair. So let's add it to our list. Okay, so all three of our basic kinematic pairs, each of them allows 1 degree of freedom and fixed 2 of those parameters. The rolling one's a little weird. One of them was clearly constrained, and the other is constrained by this equation. Any questions about our rolling pair? Yeah.
So when I choose that one of them is free, is the choice arbitrary, or is there a specific one that I'm supposed to hold? And if so, the case that there's one that I'm going to hold specifically, which case would that be? Is it gears, or is there a specification?
Yeah, so the question was which one is free, which one do I hold, and which one, it's arbitrary, and it's up to you. And where we're going with all of this is towards calculating mobility, which is going to tell us for an entire mechanism, once we look at how many links and how they're connected with these different types of kinetic pairs, how many different inputs are there for the whole mechanism? And it's not going to tell us which input is where, right? You can actually move a mechanism in lots of different places. Think about the car. You can move a car forward by, by pushing on the back bumper. You can move it by pulling on the front. If the steering wheel's turned, you could probably move it by pushing on the side. Right? Those are all different inputs, but they all move the car in the same way. And similarly, if this is our entire mechanism, a little sneak peek, the mobility of this mechanism, just a wheel rolling, is 1. Right? There's one free parameter. It could be x that you're moving, or it could be theta. But mobility is 1. Okay, let's look at our last kinematic pair, and then we'll get to calculating mobility for multi-link mechanisms. They're not so interesting when it's just a single link like this. Okay, last one, roll plus slip. So while I'm erasing, think about roll plus slip. Think how many parameters are free, how many are going to be constrained. Okay, so roll plus slip, I'm going to do the exact same drawing, but it's just going to be allowed to slide as well as roll. So we don't always have to write this, but I'm going to write that slip is occurring there. So if you take your hand, put the chalk down. Right, this is our roll plus slip. If you take your hand out and use your fist as the wheel, roll plus slip could be like this, sliding along your hand. Right? It can roll and it can slide. Any of those motions are allowed with a roll plus slip. that's what's happening here. So we have our parameters x, theta, and y is constrained still, right? It can't lift off from the ground. That's implied by our kinematic pair. So this type of kinematic pair constrains y. But just due to the nature of roll plus slip, right? X can move. Like if you hold theta, x can increase. The whole thing can just slide left and right. Or conversely, you can hold x constant and you can rotate it in place. That would be slipping. You can do either of those. So y is constrained, but x and theta are free. Okay, and this makes sense, right? It's a combination of a sliding and a rolling kinematic pair. And if we look up to our rolling pair, it's the same thing, except our equation is violated now. X equals r theta. It's violated. So if it starts slipping, that means that x equals r theta is broken now. Okay, if it wasn't slipping, it turns back into a rolling pair in that equation. So that equation kind of enforces the no slip condition. But that's violated here. X and theta are free. So this one, the motion is more complicated, but I think our conclusion is simpler. This means there's 2 free degrees of freedom. So this roll plus slip, roll plus slide kinematic pair is a 2 degree of freedom kinematic pair. Okay, so that completes all our links. Questions about this one? All right, so let's get to our conclusion here. Let's define our mobility based on what we've learned, and let's see how we can calculate it. So mobility is going to be true for a mechanism. So one mechanism has one mobility value. So for a mechanism, we need to know how many links are there, right? We know that each link has 3 parameters to start. So we need to know the number of links. We'll call that lowercase n. So let's calculate this. We know I've already given you all the building blocks. So we're not going to think about an abstract mechanism. We're just going to think about what we've learned for individual links. So mobility for a whole mechanism, each link starts with 3, right? Each link started with, in this case, x, y, and theta. So let's do that. That's 3 times our number of links. But number of links, you know that I've set this standard since last week, where the ground counts as link 1. So let's just remind ourselves here. So if you count the ground as link 1, the ground is fixed already, right? The ground has mobility 0. It's not moving at all. It's totally constrained. So if we've counted the ground as link number 1, we need to subtract that out. So let's do just n minus the ground, n minus 1. Okay, so that's how it would start. If we had multiple links that aren't connected together, with no kinematic pairs, this would be our mobility, 3 times the number of free links. But we're going to constrain some of those free parameters by kinematic pairs. Okay, and we have a list of them up here. So every time we have a turning, sliding, or rolling pair, we're going to subtract 2. Right? It constrains 2 things and leaves 1 free. So we're going to subtract, and the book uses this letter J. So J1, that's our number of 1 degree of freedom kinematic pairs. Okay, so for every turning pair, you're going to subtract 2. For every sliding pair, you're going to subtract 2. For every rolling pair, you're going to subtract 2. Each of those constrains 2 parameters. Okay, and I know it's confusing because it's kind of inverse here. But for sliding and rolling, each of those constrains one parameter. So we call those J2s. That's our number of 2 degree of freedom kinematic pairs. Okay, so nothing too crazy going on here. It's the same process we did over here for each of these kinematic pairs individually. Each of them subtracts either 1 or 2 parameters from our free list. So most of them subtract 2, but slide plus roll only attracts a single from our a single integer from our mobility. Yeah, question?
Is the mobility just the degree of freedom of the whole thing?
Yeah, the question was, this is right. The mobility is the degree of freedom of the entire mechanism. And sometimes you'll hear mobility. I'm not going to use this term, but sometimes you'll hear mobility referred to as degrees of freedom of the mechanism. Yeah, that's a good way of thinking about it. Any other questions about our mobility definition? I'm going to add one last thing to this, which we'll come back to not today, but in the tutorial. Robin will touch on it, and in the next lecture. I'm going to add one thing here, which is n subscript r, because sometimes we get into a little bit of trouble. And nr is the number of what we call redundant constraints. Redundant constraints. And basically, I'll give you a sort of a really basic example of a redundant constraint. And in the tutorial, Robin will show you some more examples, and I'll give you one more in the next lecture. And this has to do with how you're counting up your kinematic pairs, right? We need to find J1 and J2. These are integer numbers of kinematic pairs. I'm going to draw a sliding pair like this. Okay, we have 2 links. We have one sliding pair. So we'd say n equals 2. J1 is 1. There's one sliding pair, or one degree of freedom kinematic pair. Okay, there's no roll plus slip. That one's kind of unusual. We don't see it as much. So if we calculated our mobility, okay, we'd come out with, this is our first mobility example, 3 times 2 minus 1 minus 2 times 1. So we get 3 minus 2. We get a mobility of 1, which is good. That's what we expect. This thing can move back and forth alone. But what if someone else came along? So that's an example where everything works out just fine. What if your friend came along and said, oh, no, I like to draw mine like this. Right? There's a slide on the bottom. There's a slide on the top. And they said, actually, there's 2. Right? There's 2 sliding pairs. It's sliding on the bottom and it's sliding on the top. In that case, we'd say n equals 2. J1 equals 2 now instead of 1. J2, that's our number of 2 degree of freedom kinematic pairs. That still equals 0. Okay, so in this case, mobility, let's calculate it. 3 times 2 minus 1 minus 2 times 2. Mobility is 3 minus 4, and we come out with negative 1. Okay, negative 1 is a number you shouldn't get. Like 0 should be the lowest that you come out with mobility. It can't be lower than 0. That just doesn't really make sense. We know that this mechanism should be able to move. The mobility should be 1. But we overcounted, right? Your friend said there's 2 sliding pairs, which is true, right? You look at it and say, yeah, they're right. There's 2 sliding pairs. But the fact that those sliding pairs are parallel means that they're doing the same thing, right? They're redundant. So this second, counting this as a second kinematic pair is redundant. Okay, so sometimes this will happen, and sometimes it makes sense, and sometimes it doesn't. And this is basically a fudge factor, a correction for when that happens. Okay, and sometimes, like this one I think is pretty obvious that that was not a good choice to count it. Other times, things like gears or other types of some weird mechanisms, we'll show you some examples. This will happen a little less expectedly, and your mobility will be too low, and you'll have to hunt for those redundant constraints. Basically, both of these constrained the height. So the height was constrained twice, and the angle was constrained twice, right? You can't constrain the same thing twice. So in this case, our redundant number of kinematic pairs was 2. That was for the height, like y, and the angle theta. Okay, so we'll come back more to those later. These are tricky to find sometimes. We don't have an equation that's going to tell you when there's these redundancies. But the good news is they crop up in a few common scenarios. So double counting or looking, just adding a kinematic pair when it's already there, hidden, is one way. And a few other examples like gears, you'll be able to sort of spot some of those, and we'll point out some of the common ones so that you can identify them. Any questions about our redundancies for now?
Here.
Yeah.
For the sliding pair, is it only one redundant constraint? It's only one?
Number of redundancy, NR is 2, because the correct mobility should be 1. It can move horizontally. X is a free parameter. So we calculated -1. So to get it back to the correct value, you need to add 2.
Okay.
You need to add 2. Yeah. Yeah. Okay, one last question on this?
I'm not sure I understood what J1 and J2 are.
Okay, guys, we're going to do one quick example left in the last 2 minutes. It's going to be real quick, but I'm going to answer this question first, which was just about J1 and J2. These are integer number of kinematic pairs. The example I'm going to show you, you'll see what I mean. We're just going to do a 4-bar real quick. It'll take us 2 minutes to do this as our first example. So let's just draw our 4-bar that we've seen a couple times already. Okay, and we're going to count up n number of links. We're going to count up J1s, and we're going to count up J2s. So let's just number our links. I've already numbered them for you a couple times, 1, 2, 3, 4. I often have had questions, should we number the ground multiple times? Right? The number of links is important. So you need to think one piece of material is one link. So the ground is all one piece of material. So don't count this ground as number 5. It's all one ground. So that's number 1. So our number of links here, including the ground, is 4. Okay, and now we're going to count up our J1 and our J2 values. So these are integers, and it's just the number of 1 degree of freedom and 2 degree of freedom kinematic pairs, right? And right hidden behind here, sliding, rolling, or turning, those are all J1s. So the only time you're going to see J2 is a slip plus roll. That's the weird one. You'll probably realize it real quick when you see one, something that's doing a weird motion. So J1s. What kind of turning pairs do we have here? No sliding, no rolling. It's only turning. So we have 1, 2, 3, 4. So we just go through and count them. J1 is 4. J2, there's no slide plus roll. I'll tell you right now, this one has no redundancies. I know that from experience. You'll get some experience and develop that on your own. So we can just use our equation now and calculate our mobility. It's going to be 3 times n minus 1, which is 4 minus 1, minus 2 times our number of J1s. So each of those turning pairs restricts 2 parameters. So we're going to do 2, right? 2, 2, 2, 2 parameters restricted. And this is all we need to do to calculate mobility. We come out 9 minus 8 is 1. Okay, so our 4-bar mechanism, a single input If I want to constrain this mechanism, I can hold link 4 angle, and the whole mechanism will be fixed where it is. That's what that mobility of 1 means. Okay, check out the tutorial tomorrow for some more examples, and we'll also do some more examples in lecture briefly. Thanks, everyone.